Welcome everyone. During this lecture we're going to introduce a very important concept related to rotational motion called torque. We'll define the moment arm, we'll discuss the three conditions for static equilibrium, and we'll also introduce a static equilibrium application involving a hinged crane. Let's begin with the definition of torque. Torque is a measure of the ability to change an object's state of rotational motion. And I'd like to emphasize the word change because objects have a natural tendency to maintain their motion. In fact, when we attempt to change their motion, the objects will resist that attempt. In fact, according to Newton's first law, an object in motion tends to stay in motion, and an object at rest tends to stay at rest. And this applies to one-dimensional motion, two-dimensional motion, as well as rotational motion. And so, in order to change an object's state of rotation, torque must be applied. Let's now explore the mathematical definition of torque. Let's begin by considering a lug nut that's been thoroughly tightened onto the wheel of a car. Now, if we had a flat tire and we needed to take the wheel off, we wouldn't imagine trying to take this lug nut off with our fingers. And that's because our fingers cannot apply enough torque to loosen this nut. Of course, we would reach into the trunk and hope that we have a wrench. Well, I found a wrench, and of course, in order to loosen this nut, we need to apply a force. The wrench won't loosen the nut on its own. Now, if you've used a wrench before, you know that the location and the direction, as well as the magnitude of the force, all play a very, very important role. If we applied a force in a direction that is parallel to the wrench, we know that this force will not enable us to loosen this nut. On the other hand, if we applied a perpendicular force, this force would enable us to loosen this nut. And by the way, let's assume that we need to create a clockwise rotation on this nut in order to loosen it. This would only occur if the nut had a reverse thread. However, this assumption will simplify our analysis. Let's consider what happens if we move the force to a different location. What if we move the force to this location, closer to the nut? Well, again, if we have experience with a wrench, we realize that if we move the force to this location, we're going to have to exert a lot more effort in order to loosen the nut. In other words, the magnitude of the force will have to be higher than it was at the end of the wrench. And so the distance from the nut is very important. So how do we quantify torque? In order to answer this question, let's apply a force at the far end of the wrench. We're going to label that force as F. And let's also note that this force makes a certain angle with respect to the axis of the wrench. We're going to label that angle as theta. Now, earlier we noted that if we apply a parallel force, that force does not enable the rotation of the nut, whereas a perpendicular force does. Well, this force has two components. One of them is parallel, and we can label it as F with two parallel lines. That stands for F parallel. And the force also has a perpendicular component that looks like this. We're going to label that as F perpendicular. We also noted that the location of the force is very important. In other words, the closer we are to the nut, the more difficult it is to loosen it, whereas the further out we are, the easier it is to loosen the nut. Let's mark that distance between the center of rotation of the nut and the location of the force as R. We're now ready to develop the equation for torque, starting with the symbol for torque. The symbol for torque is the Greek letter tau, which looks like the letter T with a curved top. And the equation for torque looks like this. First of all, the force is very important, but not the entire force, because the parallel component, again, does not enable rotation, whereas the perpendicular component does. And so torque is directly linked to the perpendicular component of force. Also, we noted that the distance from the center of rotation to the location of the force is very important. Therefore, the greater the distance, the greater the torque, and there is the first definition of torque. Let's construct a triangle now for the force and its components. That triangle would look like this. Here's our force. Here's the parallel component, and this is the perpendicular component. And of course, this is our angle. From this triangle, we can note that the perpendicular component is the opposite side, and of course the opposite side is related to the sine of this angle through the following relationship. We know that F perpendicular just equals F times the sine of theta. Let's substitute this result into the torque equation. This yields torque equals F sine theta times R, which is typically written as F R sine theta. That is the general torque equation. In this equation, R is called the moment arm. And the word moment just means leverage. And so you can think of R as the leverage arm. And once again, R is just the length of the line that connects the center of rotation of the object to the application point of the force. Theta is the angle formed inside the X between F and R. And let me discuss that a little bit further. So again, theta is any angle inside the X formed by the extensions of F and R, and we're going to look at an example of what is meant by this definition. In our example, the force looks like this, and R looks like this. Next, we will extend R and we will extend F using dotted lines. So here's the extension of F, and here is the extension of R. As you can see, we formed the letter X. And the angle that we've defined in the torque equation is any angle inside of this X. And so the angle is defined here. It's also defined here. It's defined inside of this part of the X as well. And finally, there's another angle that can be used inside of our equation. And so anytime we form that X, any one of these angles could be used within the torque equation in order to yield the torque. Now, of course, really we only have two different angles because the angle here and there are equal, and the larger angles within the X are also equal to one another. So we can label these as theta 1 here and theta 1 across from it. The other angles can be labeled as theta 2. Of course, the angle across from it is also theta 2. But the point is this: any one of these angles can be used in the torque equation, and the result will be the same. We will now discuss the formal definition of the moment arm. The moment arm which of course is abbreviated as R, is the length of the line that joins the following 2 points. The first point is the center of rotation, and the second point is the force's point of contact. If we refer to our wrench diagram, we could see that R meets this definition. In other words, it's the length of the line that joins the center of rotation, which is right here, to the contact point of the force. Let's introduce the units for torque. From our torque equation, we note that the torque equals force times displacement times the sine of the angle between the two. Now, in the SI system, force is represented in newtons, and R, which is the moment arm, is represented in meters. So the SI units for torque are the Newton meter. And in the British system, force is represented by pounds, and R, which is length, is measured by feet, and so the foot-pound is the unit for torque in the British system. There's also a sign convention for torque. When an applied torque is attempting to cause a counterclockwise rotation, that torque is considered to be positive. And so for counterclockwise, rotation, torque is considered to be positive, and for clockwise rotation, the torque is considered to be negative. There are two additional considerations that must be taken into account, and we'll label them as Note 1 and Note 2. When a force's line of action passes through the center of rotation, the torque produced by that force must equal 0. For example, if we consider the application of a force onto the screen of a laptop computer, there's our laptop computer, there's a hinge located right here, and if we applied a force onto the screen like this, that force is incapable of rotating the screen, and that's because the force's line of action passes through the center of rotation. In fact, we can indicate this by drawing the line of action. That's the force's line of action, of course, and the force is directed right along this line, which passes right through the center of rotation. Therefore, the torque associated with this force equals 0. If we call this force F, then the torque produced by that force must equal 0. Again, the force doesn't equal 0, but the torque does equal 0. Additionally, whenever two objects are connected, each will produce a force upon the other at the point of contact. This is known as the reaction force. And this force is abbreviated as R. The reaction force will be represented by its x and y components. Which we will label as r sub x and r sub y. Within our free body diagrams. The torque produced by Rx and Ry will equal 0 at the point of contact. And that's because Rx and Ry are located at the point of contact, which means the length of the moment arm equals 0. We will now introduce the three conditions for static equilibrium. When an object's state of motion is static, let's recall what static means. Of course, static means that the object is either not moving or it's moving with constant velocity. In other words, it cannot experience acceleration. Three conditions must be satisfied. The first condition states that if we add the torques about some center of rotation, that sum must equal 0. The other two conditions are familiar to us. The second one states that the sum of the forces in the x must equal 0. And finally, the third condition states that the sum of the forces in the y direction must equal 0 as well. Let's emphasize that when we evaluate torque, we must consider three ingredients, and they are force, moment arm, as well as the sine of the angle between the force and the moment arm. We will now consider an application of the static equilibrium principles. In this application, a crane consists of a 250 kilogram horizontal beam with a length of 18 meters and a cable which support a 450 kilogram load. The uniformly distributed beam is connected to a column via a hinged connection located at point C as shown below. We need to construct a free body diagram for the beam, and in part A we need to determine the torque produced by the load with respect to point C. Let's first of all note that point C is located right here at the hinge. This is the beam's center of rotation. Of course, the beam is free to rotate about this center of rotation. The beam has a mass of 250 kilograms, which means that the beam has a weight, and that weight needs to be represented in the free body diagram for the beam. Also, the beam supports a 450 kilogram load, which is located right here, and there's a tension connected to the beam, which helps to maintain the beam's static equilibrium. Finally, let's also note that there's a reaction at the hinge location between the vertical column and the beam. In other words, the vertical column creates a force at this center of location. We call that the reaction force. We will represent the reaction force in terms of its x and y components, labeled as R sub x and R sub y. Let's begin by constructing a free body diagram on the beam. Here's our beam, and we will now represent all of the forces acting on it. Let's start on the far end and note that the cable exerts a tension onto the beam, which is directed along the line of action of the cable. That tension can be represented like this. And of course, the angle between the tension and the beam is 15 degrees. We also have the 450 kilogram load, and in order to represent the effect of the load, we have to calculate the weight of the load first. And so on the side, the weight of the load just equals mg. The mass, of course, is 450 kilograms. And the result equals 4,410 newtons. And so the load could be represented like this. As we noted, the beam itself has a mass of 250 kilograms, and in order to represent the effect of this mass, we need to calculate the weight of the beam. Of course, the weight of the beam also equals m times g. The mass equals 250. G, of course, equals 9.8, and the result equals 2450 newtons. The weight of the beam must be drawn at the center of the beam, and that's because the beam is uniformly distributed. That means that the weight appears to be concentrated at the center of the beam. And so we will represent the weight of the beam with this arrow. Let's consider the reaction between the vertical column and the beam itself. Of course, this is the vertical column and this is the beam, and they're connected through a hinge connection, and because of that, the vertical column will exert a force onto the hinge. The question is, do we believe that the reaction force in the y direction is directed upward or downward? We will guess that the y component of the reaction force is directed upward along y. The upward reaction is called R sub y, and it could be represented like this. We also need to determine the direction of the x reaction, and it would probably be a good guess to assume that the reaction in the x direction is directed towards the left. And the reason I say that is because let's notice that the tension in the rope has an X component that's directed towards the right. In other words, the rope is attempting to push the beam towards the right. The fact that the beam is in static equilibrium means that the most likely event is that the hinged connection is pushing the beam towards the left with a force known as R sub X. And so we will represent that force as follows. Now, if we choose the wrong direction, that's okay, because the answer will contain a negative sign in front of it. And whenever we obtain a negative sign, the magnitude is still correct. However, the negative tells us that we chose the wrong direction for either R sub Y or R sub X. As part of our preparation, let's also isolate the tension within a Cartesian coordinate system. Here's the tension, and we need to identify the angle that it makes with respect to positive x, which is this angle right here, and it just so happens that this angle, coincidentally, equals 15 degrees. That's not always the case, but it is the case for this problem. So this is a 15-degree angle, and we would like to now identify the x and y components for the tension. Of course, this represents T sub x, and this arrow represents T sub y, and from trigonometry, T sub x will just equal T times the cosine of 15 degrees, and T sub y will equal the tension times the sine of 15 degrees. And the reason we're processing the components of the tension is because we will need to analyze the sum of the forces in the x as well as the sum of the forces in the y. And of course, Tx and Ty will play a role within those summations. Finally, we need to identify the distances between each of the forces and the center of rotation, because those distances play a role in the torque equation. Now, the distance between the center of rotation and the beam is exactly half of the length of the beam, and as we can see, the length of the beam is 18 meters, so the distance towards the midpoint would equal 9 meters. The distance out towards the load was given as 12 meters. And finally, the tensions connected at the end of the beam at a distance of 18 meters. And that is the completed free body diagram. We're now ready to evaluate the problem. In part A, we would like to determine the torque produced by the load with respect to the center of rotation, which we labeled as C. So here's our load, and we need to evaluate the torque that's produced by it. We'll label it as the torque of the load, and of course the torque of the load simply equals the force of the load times the moment arm times the sine of the angle between the force and the moment arm. Now the force of the load equals the weight of the load. We also need to consider whether the torque is positive or negative. And we're going to choose one of these. In order to make this determination, let's see what the load does to the beam. Here's the load, and as you can see, the load tends to push the beam in this direction. The beam, of course, is free to rotate about this center of rotation, and if we apply this force, the beam would rotate in a counterclockwise direction, right? If this beam was free to rotate, the load would cause this type of rotation, and this type of rotation is a counterclockwise rotation. We noted earlier that counterclockwise is assigned a positive value for torque. We noted this when we discussed the sign convention for torque. And again, counterclockwise rotation is considered positive and clockwise rotation is considered negative. And so we will choose the positive in relation to the torque of the load. And so the torque of the load simply equals positive weight of the load times the moment arm times the sine of the angle between the weight, in this case, and the moment arm. Now, the weight of the load from our free body diagram equals 4410. The length of the moment arm needs to be determined as well. Now remember, the moment arm is the line segment that joins the center of rotation to the contact point of the force. We established this fact earlier. As you can see, the moment arm is the length of the line that joins the center of rotation to the force's point of contact. Now, of course, this is the center of rotation, and the contact point for the load is right here. We can make a little dot there, and if we connected those 2 points, the length of that line segment is the moment arm. Now, of course, we can see that the length of this line segment simply equals 12 meters, and that is the value for R, which is the moment arm. So R equals 12 in this case, and the angle between R and the weight needs to be determined. Well, as we can see, R is perfectly horizontal and the weight is perpendicular. It's perfectly vertical. Therefore, the angle between them is 90 degrees. The result equals positive 52,920. And the units for torque are Newton meters. Let's emphasize that the positive means that the load tends to rotate the beam in a counterclockwise direction. In part B, we need to determine the tension in the cable. And in order to do so, we're going to apply the first condition of static equilibrium. The first condition of static equilibrium requires that we apply this principle. In other words, the sum of the external torques about the center of rotation must equal 0. And so we'll emphasize that we are evaluating the torque with respect to the center of rotation, which is labeled as C. And the question now is, how many fingers are we going to extend from this summation? Well, according to the free body diagram, we have 1, 2, 3, 4, 5 external forces that are affecting the beam. And so we will extend 5 fingers from this summation. I've also copied our diagram for convenience, and so let's evaluate all of the torques. Certainly the cable produces a torque. We'll represent that as the torque of the tension. Next we have the torque that's produced by the load. We have to consider the torque produced by the weight of the beam. We have to consider the torque of R sub x, as well as the torque produced by R sub y. When we add all of these torques, according to the first principle, they must add up to 0. In order to proceed, we must take note that torque requires 3 ingredients. Torque equals force times a moment arm times the sine of the angle between the force and the moment arm. And so the torque produced by the tension requires a force. Now we're calling the force of the tension T. It requires a moment arm, and it requires knowledge of the sine of the angle between those two. The torque of the load requires, again, a force, but the force of the load is represented by the weight of the load. Times R times the sine of the angle between those two. The torque of the beam is represented by 3 ingredients as well. Of course, the force is represented as the weight of the beam times R times the sine of the angle between those two. Now, let's pause for a moment to consider the torque produced by R sub x and R sub y. As you recall, we noted a very important principle that states when the line of action of a force passes through the center of rotation, that force has 0 torque. We labeled it earlier as note number 1, and again, let's state it one more time. When a force's line of action passes through the center of rotation, the torque produced by that force must equal 0. We can clearly see that R sub x's line of action passes right through the center of rotation, and the line of action for R sub y also passes through the center of rotation. That means that neither of these forces is capable of rotating this beam. Let's look at this another way. Imagine that this diagram represents a door with a hinge on the end. No matter how hard we push on this hinge, whether we push in the y direction or the x direction, there's no way that we're going to cause the door to rotate. Therefore, the torque of R sub x and the torque of R sub y equal 0. And so this equation reduces down to just 3 torques: the torque of the tension, the torque of the load, as well as the torque of the beam. We also have to consider whether each of these torques is producing a clockwise rotation or a counterclockwise rotation. And so we'll introduce a plus as well as a minus in front of each of them. Again, a plus or a minus has to be placed in front of each of these torques. And let's make our choice. The tension is creating a clockwise rotation on the beam. If the only force present was the tension, that tension, of course, tends to want to pull the beam in this direction. And by pulling it in this direction, the beam would rotate in a clockwise fashion. Therefore, we have to select a negative sign in front of the torque, which represents the tension. The torque of the load was already evaluated. We already noted that the load tends to produce a counterclockwise rotation on the beam. We can emphasize that once again. If this load was the only force present, it would push the beam, or I should say pull the beam, in this direction, which of course would cause the beam to rotate in a counterclockwise direction. Therefore, we're going to choose the positive sign in front of this torque. The beam itself has a weight. Here's the weight. And just like the load, if the weight of the beam was the only force present, it would tend to pull the beam in this direction, and the beam would rotate in this direction, which of course is a counterclockwise rotation. And we noted that a counterclockwise rotation is considered to be positive. And so we'll choose a positive sign in front of the torque for the beam. Of course, these three torques will add up to 0, and we will now incorporate all of the known values into this equation. Now, the tension is not known. We're trying to find the tension. So the equation becomes minus T. The moment arm out to the tension is 18 meters. Once again, the moment arm is the length of the line segment that joins the center of rotation to the contact point of the force. The distance between the center of rotation and the tension's contact point, of course, equals 18 meters. We need to introduce the angle between the tension and that moment arm. As you can see, if I temporarily draw the moment arm, it would look like this. This red arrow represents the moment arm in relation to the tension. We can extend the moment arm as well as the tension and create an X. And of course, we noted earlier that any angle within this X could be introduced into the torque equation. Now, we know one of the angles inside of this letter X, and that angle, of course, is the 15-degree angle, and so that is the angle that we will incorporate. We chose a positive sign in front of the torque that represents the load. The weight of the load from our diagram equals 4410. The moment arm, again, is the line that joins the center of rotation to the contact point of the load. In other words, the line that joins this point to this point, and as we can see, the length of that line is 12 meters. The angle between the moment arm and the weight would be a 90-degree angle. If I'll just temporarily draw that moment arm, it would look like this. And I'm going to erase it in just a bit. But just so we can visualize, this is the moment arm in relation to the weight of the load, and the angle between those two is 90 degrees. You may have noticed that we already calculated the torque of the load, and that this expression right here is identical to the work that we did in Part A. In fact, there's the expression once again. We could have just incorporated the 52,920 into this equation, but I decided to repeat this calculation just for the sake of consistency. Next, let's evaluate the torque of the beam, which starts with the introduction of the weight of the beam. The weight of the beam is 2450. And we assigned a positive value to the torque of the beam because the beam tends to create a counterclockwise rotation. the moment arm out to the weight of the beam, of course, is the line which joins the center of rotation to the contact point of the weight of the beam. I'll draw that temporarily. This is R out to the beam, and the length of this moment arm is 9 meters. Also, let's note that the angle between the moment arm and the weight is 90 degrees. Again, the length is 9 and the angle is 90 degrees. If we add all of these torques, the result must equal 0. So let's process the problem using a calculator. The first term results in 4.659 T. The second term equals 52,920. And the third term equals 22,050. That sum must equal 0. Next, let's transfer these two values to the other side, and of course their signs will change, and we can add them on the other side as well. That will result in negative 4.659 T, and on the other side we have negative 74,970, and by dividing both sides by negative 4.659, we're able to obtain the value for the tension. And that value equals 16,091 newtons. This is an extraordinarily large value when compared to the two loads that are being supported by the cable. In other words, the cable is supporting the load as well as the weight of the beam. If we add these two together, they only add up to about 7,000 newtons. So why is it that we need 16,000 newtons of tension to support a relatively low load? And the answer has to do with this angle. This is a very small angle. It's a 15-degree angle, which means that the Y component of the tension is relatively small when compared to the overall tension. And of course, it's the Y component of the tension that counteracts the weight of the load and the weight of the beam. Therefore, we need a very large tension in order to get a relatively small Y component to counteract these two loads. Let's evaluate part C of the problem. In part C, we need to determine the X and Y components of the reaction force at point C. And of course, we labeled these two components as R sub X and R sub Y. In order to determine R sub X and R sub Y, we're going to apply the second two conditions. In other words, condition 2 and condition 3 of the static equilibrium conditions. So we need to find R sub X and R sub Y. And let's introduce our free body diagram once again for convenience. In order to determine R sub X, the second condition will be applied. The second condition of static equilibrium states that if we add the forces in the X direction, that summation must equal 0. And so, the sum of the forces in the X must equal 0, and the question now is, how many fingers are we going to extend from this summation? Well, certainly the tension has an X component, the weight of the load is directed purely on Y, the weight of the beam is directed purely on Y as well, as is R sub Y. The only other force that is affecting the X direction is R sub X, and so we have two fingers that must be extended. One of them represents T sub X, and the other one represents R sub X. Now, let's notice that R sub X is directed towards the left. Therefore, it must be introduced with a negative in front of it. We noted earlier that T sub x equals T times the cosine of 15 degrees. We just determined that the value for the tension equals 16,091 newtons. Let's transfer r sub x to the other side. And on the left-hand side, the result equals 15,543. And so r sub x equals 15,543 newtons. This means that the hinge is pushing against the beam towards the left with a force of 15,543 newtons. If this hinge was not here, then this cable would push the beam towards the right. In order to maintain static equilibrium, we have to counteract the effect of the tension by pushing against the beam towards the left. Let's also note that the result is positive, and that means that we chose the right direction. Which in this case is towards the left. And so the positive result just means that our choice for r sub x, which again is directed towards the left, was the correct choice. R sub x is in fact directed towards the left. Let's determine the value for r sub y. In order to determine the value for r sub y, we will apply the sum of the forces in the y equals 0. And once again, we have to determine how many fingers must be extended from this summation. So by referring to the free body diagram, let's note that the tension certainly has a component in the y direction. And of course, that y component is called T sub y. The weight of the load is directed in the y direction, in the negative sense, of course. The weight of the beam is also directed in the negative y direction. R sub y is directed upward, and r sub x, of course, is directed purely along the x-axis, so it does not contribute to the y direction. And therefore we have 1, 2, 3, 4 fingers that must be extended from this summation. Once again, we have to consider the y component of the tension, which is labeled as T sub y. We have to include the weight of the load. Now again, notice that the weight of the load is directed purely along the y-axis in the negative direction, so it's going to be incorporated as a negative value. We're going to treat the weight of the beam the same way. It's directed purely along y in the negative direction. And we assume that r sub y is pointing upward, which is of course a positive direction. And that summation must result in 0. Now, T sub y was noted earlier as T t times the sine of 15 degrees. The weight of the load equals 4410. The weight of the beam equals 2450, and R sub y is unknown. The tension was calculated as 16,091. If we add these three terms together, the result equals negative 2695. And if we transfer this value to the other side, the result equals positive 2695 newtons for R sub y. Once again, the positive means that we chose the correct direction for R sub y. And so the hinge does in fact produce an upward force on the beam. If we obtained a negative value, on the other hand, the answer would still be 2695. However, R sub y would be directed downwards. It just simply means that we chose the wrong direction for R sub y. And that completes this lecture.